Welcome back to Let's Code. I'm Chris Biscardi, and today we're going to be talking about vertex shaders in the Bevy game engine. Now, the scene you see before you is just two objects. There is a cube on top. There's a 3D cube, not just a 2D, even though it looks like that because of the way it's placed on the camera. And then there's also the plane underneath it, which you can tell from the wireframe is actually just a flat plane that we've applied a vertex shader to that moves the vertices based on some simplex noise, in this case, to make these mountains and valleys, which are really interesting to look at. And yeah, I just wanted to talk a little bit about how to create this effect. And I'm going to take this effect further in future videos. So let's get in. So first off, we've only got two files. We've got main.rs, which includes our Bevy code, and we've got land_vertex_shader.wgsl. Now, land_vertex_shader.wgsl is our vertex shader, which is mostly the same as the default vertex shader for Bevy. So a lot of these functions like mesh position local to world just come from the default vertex shader that Bevy uses for everything. And then this additional code here is what we've added to change the color and the position of the vertices on this plane. Now, before we dive into that code, let's talk through the Bevy code. So aside from all of the items we bring into scope at the top, we've got a source of ambient white light. We've got a pinkish color on the background. I've set some WGPU settings. So I've enabled the polygon mode line feature, which is required for that wireframe effect on the plane that we saw earlier. The default Bevy plugins, the wireframe plugin, which we also need for the wireframe stuff. The shader utils plugin is the library of shader scripts that provide the noise that we've been using in every video up until this point. And then this land material is the plane that we see on the bottom of the, I'm calling it a landscape. And then we animate a light around the cube. That's why you see it kind of blinking in the beginning of the video. This movement controls the camera and the cube. So we move both of them forward through space to get that nice animated, kind of like moving through the landscape effect. And change position is passing the position of where we are, specifically, I believe, the cube, into the vertex shader so that we can do an offset and things like that. I've got this ship component just to label the cube as, the ship, quote unquote. There is no ship at the moment. I need to figure out how to import a GLTF file to use that. But it seems to be broken on the main branch right now. Or I'm just not doing it correctly. Our setup function sets up all of our objects in the scene. First, we've got a 3D bundle that is set right behind the cube, and we've put movable on it. Movable is a component that our leader system will query so that we can use the arrow keys to move our cube through space, and as well as our camera. We have a directional light that kind of circles the cube, so we have a system that animates the light around the cube. And then this is our interesting part. So in our previous videos, we've taken a mesh from something like cube or from plane or something that is built into Bevy. In this case, I've defined my own struct here to make a 1,000 unit piece of land. In this case, it's just kind of like a really big plane. And then num vertices is the number of subdivisions between the edges that I want. So a higher number here will get us smoother curves, and a lower number here will get us more jagged edges. Now, because we're using a vertex shader, one of the things that I want to do is input a bunch of basically taking the positions for each vertex and inputting them as a color so that each of these vertices has a color corresponding to the position that it exists in. I find that this creates a nice effect when I'm just getting started with a project. And sometimes when I'm debugging, I'll go back and forth between this kind of like rainbowy view and the actual effect, which in this case is like a pink world. And this having this rainbow spread across all of the vertices is one way for me to know for sure that when I change the colors, it's changing to either the shader that I wrote or the defaults. So all this is doing is getting the position attributes for all of the vertices. We get them as a vec3. So it's a 3-item vec of float 32s or F32s. And that comes back to us as positions as a vec. We map over those. We use each of these values as a color value, and then we collect it back into a vec and set it as the color attribute instead of the position attribute. And when I disable the vertex shader later, you'll see these colors come through. So this is where we're defining them. We also have to spawn the land in as a mesh. So We add the meshes, we give it a position. In this case, it's like slightly below the cube. And then we instantiate our land material, which is the struct that will control which shaders are used to apply to this mesh. In this case, I pass in time because I always like to use time, but in this case, we're not using it yet. And we're also passing in the ship position. So that's the XYZ coordinate of the transform for the cube in world space. Then, of course, we've got our cube. It's a standard material, so we could, texture it if we wanted to or whatnot. This is going to get replaced with a GLTF scene in the future. So, yeah, not much to say. It's a cube. It's kind of small. It's less than a unit, and it's placed in front of the camera. We'll also have movable on the ship, is what I'm calling it, as well as the camera. So if we move forward in tandem. The animate light direction we've gone over in the past, basically moving the directional light around the cube. That's what causes it to look like it's flashing a little bit or slowly as the light rotates around the cube. Change position is the land material. So we get the land material assets, we iterate over them. For all of the land material assets, we pass in the current position of the ship. We get the transform for any entity that has the ship component. In this case, that's the cube. So wherever that ship is in world space, we take that XYZ coordinate and we pass it into the ship position on our material as a vec3. This is the really interesting part. We've got the material implementation for land material. This just points to the vertex shader. You can see that I have some scaffolded coding here for the alpha value or the fragment shader or whatever in case I want to do that in the future. And then we've got the land material here. The land material has an arbitrary UUID, just needs to be unique, basically. We derive as bind group and the other things we need. And we define time and ship position as uniforms. So time is an F32 and ship position is a vec3. Uniforms, again, are read-only data that are sent to all of the sort of processing units, right? So when we're programming for the GPU, any pixel can be processed anywhere on the GPU, basically, because they all get processed extremely in parallel. And uniforms are basically the data that gets copied to send to wherever the processing is happening. So in this case, we get a read-only timestamp and a read-only ship position for each of the shaders, or for each of the shaders that is being processed. So in contrast to the land material, we do have this land struct. The land struct defines a size and a number of vertices like we went over before. And then we implement from land for mesh. From and into are really interesting traits in Rust. But basically, if we have a land, we can turn it into a mesh by using this from function on the land. In this case, all I'm doing is taking the plane size and dividing it by 2 and treating that as either the positive or negative maximum for the plane. So if you imagine a plane as like a square on a XY like coordinate grid, the negative most X value and the negative most Y value are going to be in the bottom left square of that XY coordinate grid, whereas the positives are going to be in the top right. If X is positive and Y is negative, it's going to be in the bottom right and so on. So if, say, you've got a 1 unit plane, the bottom left coordinate is going to be -1 for X and Y. It'll be 1, 1 in the top right for X and for Y, and then some combination of the two for the other two X and Y positions. So if it's in the top left, it's -X and +Y. If it's in the bottom right, it's a +X and a -Y. So that's what extent is here, because we're trying to place this plane basically in the middle of that XY grid. Jump takes the number of vertices that we've defined. So if we have, say, a plane of size 10, and we want 10 boxes to be subdivided out of that, so basically 5 on each side of the middle line, this is the increment to go from 0 to 1, from 1 to 2, 2 to 3, across the X and across the Y at the same time. Now, to create a mesh, we actually have to create all of the triangles ourselves. So for the vertices, we get to just do 0 to num vertices, so whatever number we passed in, and then we Cartesian product that with 0 to num vertices. So if this is like 0 to 10 and 0 to 10, then what we get back is a YX combination of all of the points in a grid, basically. So we'll get 0, 1, 0, 2, 0, 3, 0, 4, etc. We map over all of those points, and we create 2 triangles out of each of them, basically. We map over all of those points, and we say, okay, each of the increments that we need 1 of them. We do need to move the increment to the left by half of the width of the plane that we're working with. So when we're thinking about x times the increment number, we're using that as kind of an absolute number from 0 to 10, but we need it to be from -5 to 5 to fit in the middle of the xy coordinate grid. So we do x times the increment, and then we subtract half of the width of the plane. This second array value, or the second tuple value, is the normals. So in this case, all of our triangles are pointing up. So we've got the x value, the y value, and the z value. So this is basically the vector. If we drew a vector straight out of the plane itself, which direction would it be facing? It would be facing straight up in the y coordinate space. And then we set our points as basically x and y out of the number of vertices. So instead of making the plane bigger, if we have more vertices, we're subdividing the plane. So we need to be at, let's say, if we are a plane of size 10, we need to have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And we collect that into a vec and use it for any of the rest of the calculations that we need. Now, the other complicated piece of this is that now that we have all of the vertices for our plane, so if we've got like a 10 by 10 plane, we've got 100 vertices, right? We need to create the indexes for all of the triangles that make up that plane. So if we have 100 squares or 10 squares or something like that, then we're going to need to split up all of those squares into triangles. So every square can be made of 2 triangles. And that's what we're doing here. We're basically, if we have one square and say we've got points 0, 1, 2, and 3, we can draw a triangle by going 0, 1, 2, and then a triangle from 0 to 3, for example. So that's what this is doing. We're getting all of the points again using Cartesian product. We enumerate over them to get which index they are at in the list, because we do need one single list here. And then we do a filter map if we are at sort of the edges, so the very rightmost edge or the very topmost edge, then we can't draw a triangle from there to anywhere, because we're going kind of from the bottom left to the top right. So if we are, for example, all the way on the right side of x, there is no like x plus 1 for us to be at. So these are basically taking the index and pointing to each of these points. So if we have a row of 10 vertices, for example, and then we have, and we're at, say, like 0.0, we can draw 2 triangles. In this case, we would draw 0. So if we look at these in more of a visual representation, we can see that if we say start at this point, we can draw a triangle by going across and back. And that gives us this point, and that point, which defines this triangle. And then we can also go from, say, this point, and that point, which defines the other triangle. And then we get 2 triangles for this whole square here. The math is a little fiddly. It depends on kind of what order you have your vertices in. And it also, if we scroll down a little bit, we use flatten twice, by the way, because we return sum and then an array of 2 points or 2 triangles. We want to flatten all of that into a single list because we're using triangle list here, which is a single list of 3 points next to each other. So we would have one vec of 0, 1, 2, 0, 2, 3, and that would be 2 triangles, but it would be one vec, which is a little bit confusing, but that's just the way we have to pack the data. So we get all of the positions for all of the vertices, we get all of the normals for all of the vertices, and we get all of the UVs for all of the vertices, which is what we've defined above. Actually, did we get to UVs? Oh, I don't think I explained UVs correctly. UVs are, say we have a plane, 0, 0 is in the bottom left, 1, 1 is in the top right, and then that's our UV coordinate space. So that's what this X and Y are. It's UV coordinates. It's not necessarily point coordinates on the XY plane that we are thinking of. It is its own space, right? When I say world space or UV space, this is defining a space that starts at 0, 0, ends at 1, 1, and represents the entire plane that we are working with. So for all x's, we have to be like, if x is 0, then we're at 0 over number of vertices. If x is 5, then we are at 5 over the number of vertices. So if we have 10 vertices, we're halfway through, that kind of thing. And then we set the indexes on the mesh. We set the attribute, we set the position of the vertices on the mesh, and we set the normals for all of the vertices. Now, it's confusing here because everything is kind of set in a different place and the ordering matters and all of that kind of stuff. But maybe I'll do another video on a more produced video of what it takes to actually create this mesh, because it is a little confusing, and it took me a few tries to create the triangles correctly. So that seems like something worth doing. And then we've got movable, and anything with the movable component on it gets picked up by this movement system, and we move either plus or minus in the Z direction, or plus or minus in the X direction, using the arrow keys, as we've done before. So if we go back and we look at our demo here, we can go left and right and forward and back, and all of that still works. Now, as I move forward here, you can see a little bit of a up and down bump. That's attributable to the sine calculation that we're about to see in the fragment shader. So to start with, we're going to take the vertex position and we're going to create a noise value out of it. This is the value that is going to give us either the high mountain or the low valley for our y coordinate. Remember, this noise value is going to be from -1 to 1. And then we set the color of the vertex to RGB alpha using a vec4. Again, we don't have like complicated types here. We just have a vec4, and we can pass kind of any information that we want to out of this. In the past, we've actually passed the position here to access that in the fragment shader. But in this case, it's half red, whatever noise value we have, and then half blue. And this is from -1 to 1, right? So if you look at the color values that are below 1, they're kind of all like very saturated out and washed out, and like they all look kind of the same. That's what gives us this little bit of like fog-ish effect down there. I can take the mesh off later too and show that a little bit more. So then the world position of the vertex. So the position of the vertex as it stands in the actual entire game scene is created by passing in the model, which has our mesh information on it, and then the vertex position for X, the vertex position for Z, and the noise value for Y. And this noise value for Y is how we get the peaks and the valleys in our vertex position. Now, I've done some additional stuff here. So to get the noise to behave a little bit differently as the ship moves through, I've taken the ship position, and you can see that I've calculated the offset from where the ship is to where in the world we are. And I've applied a sine wave to that with an amplitude of 4. So if you multiply 4 by a sine wave, you get a bigger amplitude, right? Because sine goes from -1 to 1. So in this case, we'll go from -4 to 4. We divide that by 100. Seems like a good number. It's arbitrary. This is a magic number here. And then we set the new world position to the old world position minus that value. So I'm trying to get this kind of up and down effect. And I might switch this to be something a little bit more like world curvy. So instead of seeing the vertexes go up and down here as they're traveling past our cube, we could have this sign be the total representation out to the end and be kind of like a world horizon instead of this flat horizon that we have sticking out from our plane. And then we do the same for clip position. I'm going to be honest, I don't quite understand the difference between clip position and world position. I think clip position has something to do with when the stuff on the screen stops rendering, but that is something that I left in from the default vertex shader. And actually, we can do this. If we don't include the clip position, we actually don't get any output. So critically important to have the clip position as well as the world position. But I'm going to be honest, I don't understand clip position yet. There will be a future video on what clip position is because I need to go look it up. And that's it. I mean, we've got a cube, we've got a plane, we've got the plane subdivided into triangles. We've got the ability to move on said plane. So we can go forward and back or left to right or both or a bunch of them. And this is a 1000 by 1000 plane. So we're kind of in the middle of it right now. And there are 1000 vertices. So it's kind of jagged. We can cancel that. And I want to show two things here before we leave. Let's take a look at, I don't know if this will work, if I'm being honest. Okay, my entire computer is slowing down. Okay, well, that was a fun experiment. My entire computer is slowing down. Instead of making it 10,000, let's make the size of the landmass down to 100. And we can see how 1000 vertices creates this nice, like, very smooth result compared to what we had before. And you can see in the vertices on the ground here that they are much smaller than before. So If you're looking for something a little bit more blobby, this is a better approach. If you're looking for something that's a little bit more fragmenty, I think that fewer vertices works better. Let's do one more thing. Let's move this back to being 1,000, fill the server, and then let's remove the wireframe. So here we've got a wireframe. The wireframe is on the landmass. So if we remove the wireframe from Bevy, we won't see the outline of the plane as it exists in the system anymore. And we will just get to see kind of our land masses going by. So you can see that the color below 0 kind of clips out and creates this fog effect. We don't see the wireframe anymore. We could put the wireframe on the cube as well. But yeah, I'm hoping to put a spaceship inside of this. And yeah, we'll see. I don't know. I don't know where I'm going to go with this one. But I hope that you learned a little bit about Vertex shaders. They're really cool. It's really fun to kind of mess with the position in the rendering that the vertexes are supposed to be. You could easily see this used for water or something like that. And hopefully you can see how like we can get a flat plane to look kind of mountainous and completely different without actually changing anything in the mesh. So I will catch you next time. And I hope you enjoyed this episode of Let's Code. As always, the code will be linked in the description. And if you have any questions, leave a comment. If you liked the video, drop a like. It helps out. I'll catch you next time.